Yes, we are live.
Greetings, fellow nerds. Welcome to another episode of Between Two Nerds, where we talk with prominent guests about all aspects of the networking industry, from protocols old and new to industry trends and drivers to up-and-coming technologies, and as always, things you need to know to further your career. I'm Jeff Doyle, and with me, as always, is my friend and colleague, Jeff Tansura. Hey, Jeff.
Hey, Jeff. Great to see you, as always.
Good to see you too. It's it seems like the only time we get to visit anymore is on this show. We've got a mutual friend today, our friend Aninda Chatterjee, who is Aninda actually has a couple of books out. One book out right now, and another book that's out end of May. It's real soon that it's supposed to be on the shelves, isn't it?
It's a week. Yeah, it's in a week.
Yeah. So I've been plugging this book every chance I get. Not just, I think I've plugged it on this show. This is the existing book, and I should say the title is Deploying Juniper Data Centers with EVPN VXLAN, and the next book is
Mastering Advanced Juniper.
Yeah. So, kind of two ways to approach these books. I always say, if you're doing a Juniper network, this is the book you need to be reading, if you're running Juniper in your data center, Junos in your data center. But beyond that, even if you don't have a single switch in your data center that starts with a J, this is, in my opinion, the most comprehensive book just on EVPN VXLAN on the market today. There are several out there, and you go so much further into detail, and with really rich examples in your book, in this thing. And it's not just because you're a friend. It really is. I'll tell everybody, if you want to learn EVPN VXLAN, that's the book you need to be reading.
And I agree. It's very readable. It's well written, good illustrations. If you are learning about, not only learning, even if you're an advanced learner of EVPN VXLAN, still a great book. Gives so much depth on particular topics. Very much advised.
Yeah, and it's one of those books it's organized in such a way that it makes a good desk reference too. I just need, I need to, I forgot how to do X, and this is a book you can grab and look it up very quickly.
Very high honor, guys. I appreciate it.
So today, where I kind of wanted to go with the show is because the new book, the Mastering EVPN VXLAN, focuses primarily on multicast in EVPN networks. And really wanted to talk a bit about that. We've talked a bunch about EVPN on this show with all kinds of guests, but I don't think we've ever had a show where we've specifically discussed multicast. Jeff, do you recall?
Yeah, we mostly had pure multicast people. So we had, I believe, Dina at some point in time.
Oh yeah, I forgot about that.
And then we had Juniper person from East Coast. I'm sorry, I forgot his name. He's been doing multicast with schools and everything for many, many years. He's working on this a tunneling over MBON.
Oh yeah. Okay.
Italian name, sorry, the Giuliani, something like this.
Oh
sorry,
man, I'd completely forgotten that.
But
of course, yeah. I've forgotten, what I had for breakfast this morning. So
yeah, me too. Sorry, I feel completely. Anyway, so we talked a lot about IPv4 multicast, how kind of PIM, GNP, MLD eventually evolved into what we use today as IP multicast. But I don't think we've ever kind of deep down on multicast specifically in a VPN, and potentially more details where you could use PIM, you could use a more advanced technologies, potentially point-to-multipoint LSPs, potentially beer. We've never went this particular route, so it's great that you agreed to join us and enlighten us.
Yeah,
Yeah,
that's awesome.
And we were talking before the show, and I know you've got some slides that, even though we've discussed EVP and VXLAN a lot, it's probably worth doing at least a brief refresher, just because it's not an easy topic.
Yeah, absolutely. And first, thanks for having me, guys. This is awesome. I am absolutely thrilled to be here. And like you said, we'll structure this a little bit. We'll level set the playing field. We'll talk about EVP and VXLAN, just the historical aspects, the evolution, what it looks like today.
Mm-hmm.
And I think we'll try to cover as much as we can of intra VLAN multicast today, because these topics are really big, as you can imagine. There's a lot of stuff going on. There are a lot of different designs and variations, like Jeff was talking about earlier. So we'll stick to maybe intra VLAN and see how far we can get. And then, we could do inter VLAN another day, maybe. Awesome. So we'll start way back with a lot of history, which I had to learn because I wasn't around for a lot of this. So your traditional data center architecture was typically 3 tiers. You had your cores, distributions, and your access layers. You would also sometimes see this as a collapsed core connecting to your access layers. And then things were fairly, very cleanly divided into layer 2 and layer 3. So you had your access to distribution was all layer 2 links, spanning tree blocking redundant paths, and then distribution and up, you had your L3 towards your WAN, just high speed, traffic in and out of your network infrastructure. This was fine for a long period of time, but obviously this architecture had several drawbacks, especially when you're looking at distribution down to the access. You're potentially very inefficiently using your links, because spanning tree is obviously blocking all of your redundant paths. You can muck around with STP. You could have different VLANs build different trees and try to balance it out as much as you can, but it's such an operational overhead that it's not really worth it. Anybody who's been working with such environments, I'm sure, has nightmares of debugging and troubleshooting layer 2 loops, especially when you start seeing your infrastructure move away from these STP triangles into rings, and those rings start to extend, and you figure out STP used to have a thing called a diameter, which is fun to realize when that actually breaks things apart. So I'm sure we've all been there. And then scaling up from here also is very hard, right? The impact of failures is very high, depending on how big your layer 2 domain is. And you essentially have a very disproportional investment into your network infrastructure, because you're paying for all of these speeds and feeds, but you're not really utilizing everything as much as you can from a network infrastructure point of view, right?
And I wanted to interject. I'm as guilty as anyone else. We sort of are all in the Clos architecture world, or some version of that now, and with complex data centers. And and we always refer to that 3-tier architecture as this is all old legacy concepts and all of that. But if you're building a simple data center with a lot of north-south, primarily north-south traffic, where you're serving files, you may be doing simple websites, email, and all that kind of stuff. Everything is just sort of in and out of your data center. Some simplified version of that could still be a perfectly fine a way to design a small data center.
What's funny? We've used word scale up as a negative term back then, because we didn't scale out, we would build up. Today, scale up is a very positive term. It's the hottest topic in the industry, in very different context. So it's funny how we keep reusing same terms in the industry, and every 20 years it pops up, but with completely almost the opposite meaning, right?
Yeah.
I mean,
Nothing
it's
is under the moon.
Well, like I
it's-
said, I'm as guilty as anybody of, kind of leaving the impression after, we always have that first slide. Oh, here's the old 3-tier architecture. And, and it sort of leaves the impression this is a bad thing. Don't ever do these. And there's a place for them. Anyway, just wanted to say that little nice piece about legacy.
No, I agree, because I mean, it's all, at the end of the day, it's what you can live with from an operator's perspective, right? At the end of the day, like if you're operating and you're maintaining your network infrastructure, do you have the competency to shift to EVPN VXLAN? Do you really need to shift to an EVPN VXLAN design? So those are important questions to answer. I think the way I generally position this is, these are the pros and cons of doing all of this. And I think it's good to understand both sides in order to make an informed decision of what you want to do with your infrastructure, right? And like even technologies from way back are so relevant now. Like I remember doing so much of class of service 15 years back, and with AI clusters, it's so prevalent in terms of just buffer monitoring and ECN and PFC and building lossless Ethernet fabrics, right? So it is it's very interesting the way things come back from the past. But moving on. So from a network infrastructure point of view, of course, we've had a lot of evolutions. We've moved towards things like VPC, MC-LAG, M-LAG, VSS, StackWise, whatever you want to call it, right? But you're essentially logically bundling two switches together, and you're taking away what spanning tree would do downstream, because now everything is bundled into a port channel, and everything's forwarding and hashed through multiple links. So you do make things much more efficient there. But again, this is fairly complex from a software engineering point of view. Again, I speak from a lot of experience, having been on the escalation side of this, having done this in production, having seen VSS failures over several years. Most of this is very vendor proprietary. It will change, between Juniper, Cisco, Arista, VSS, MLAG, VPC, whatever you want to call it. So there is that operator complexity in trying to maintain this long term, right?
Yeah.
That's a challenge here, unless you bring subscriber management overlock into this. I still have PTSD. It's been probably 15 years since Red kind of disappeared. Doing all of the stuff together, I mean, MC-LAG is probably the worst and most complex technology ever invented.
Yeah, because I mean, you're having to sync state. Debugging that is so hard. I agree. It is on like face value. Okay, maybe it seems fairly simple and straightforward to configure, but yeah, it is very challenging to operate and maintain over a long period of time. Now, obviously, at the same time, we've had a lot of application evolution as well. We're looking at the advent of microservices. We're looking at VMs and containers coming out. And what that has obviously done is traditionally, you would have everything in a physical server, whether it's your web app or your database. Everything is just one physical server. Now you start to see them spread out, and you start to see multiple database servers, and I have to do database sharding between them. I have multiple browser engine services, and they're all taking in multiple requests. I'm talking between all of these guys. So we essentially had a very high amount of east-west traffic that suddenly emerged versus north-south, which was traditionally seen, right? When we moved from this traditional client server to a more distributed architecture. And it sort of became a little clear that when you start to scale your infrastructure, your traditional 3-tier or even a collapsed core sort of environment was not really able to cope up with all of this, right? and that's when we started to shift and adopt different designs for our data centers. Now I want to go way back, and this again, like I learned a lot of this through Russ White, and watching a lot of what he has done, reading a lot of what he's written, and then of course like doing my own research and trying to figure some of this stuff out. So this is very interesting to me, going back and like reading the original paper that Charles Clos had written, which is actually still available to read, if you have the time to actually read it. But essentially, this is what Charles Clos did back in I want to say 1952-53. Like he was working with these large crossbar fabrics for telephony systems, right? And he was trying to figure out, how do I actually scale my telephony fabric to allow for more calls, essentially. And he realized mathematically what we can actually do is build out my fabric in stages, and I essentially connect my crossbar fabrics in multiple stages, and then mathematically, like an odd number of stages is the most efficient way to do this. And this is where he landed. He landed into a 3-stage Clos design for telephony systems specifically. So you have like an ingress stage where all of your calls come in, and then you have a middle stage which acts as a fan out, and then you have your egress stage essentially where your calls get outputted from, right? And this was the most efficient way to scale out like a telephony fabric in that day and age, right? We eventually adopted this for packet switched networks. So our ingress stage essentially was the leafs, where I have all of my services connected. My middle stage became the spines, and they essentially act as a fan out, provide equal cost paths between my egress stage, which is again my leafs, right? And when you fold this over the other, you get a very familiar topology, which we see very predominantly today, which is your spine and leaf topology, also known as a 3-stage Clos topology. And again, the 3 stages are the ingress stage, which is an ingress leaf, your spine layer, which is your middle stage, and then an egress leaf as your egress stage, right? And all of my services are essentially connected down to the spines.
That the folded concept that you had on the previous slide is something that, for people that have seen that for the first time, sometimes that can actually be
confusing.
A little bit confusing, because you have to say, we're looking at the input side and the output side. You're looking at, a unidirectional traffic flow in that diagram, but those interfaces on each side of it are the same interfaces.
Correct. Because for telephony systems, like you said, that's exactly correct. It is unidirectional, right? But for packet switched infrastructure, obviously we're working with bidirectional fabrics, so traffic can come in and go out of the same layer, which is why we kind of fold it into the ingress and egress gets folded into one layer, which is my leaf layer.
Right. Yeah. Conceptually, like in this, you're talking about bidirectional, but if you're looking at just that unfolded, is that a good way to say it? The diagram, you're always looking at everything in terms of input and output.
Yeah. So at least for me, the 3-stage Clos is largely it's guidance on like the physical connectivity of the fabric itself, to deal with the ever-growing scale of virtualization and containers and stuff like that. Purely to overcome all of my layer 2 limitations that I would have with spanning tree, right? Now, obviously, we have to build on top of this to make this a properly efficient infrastructure. That's where additional guidance comes into the picture, where instead of using layer 2 links now between my nodes, I will switch to point-to-point layer 3 links. And what that does very quickly for me is now that provides equal cost paths through my spines, right?
Probably what's important to mention, I think it's moving away from switch infrastructure as in circuit switching, as defined by Charles Clos, to packetized infrastructure where you don't need to match number of outputs to number of inputs, and how much efficiency it allows, since again there's no clearly defined, we call it non-oversubscribed fabric,
Correct.
but practically they're statistically non-oversubscribed.
Yeah.
Practically you can always oversubscribe a fabric even with similar number of inputs and outputs. But however, what's the most important part is that we moved from N input to M output from completely decoupled number of output due to IP characteristics, right? They don't have this fixed VPVC structures you would see in, I don't know, ATM or frame relay switch.
Yeah. Oh man, ATM and frame relay. That was I was around for frame relay. I was absolutely not around for ATM. I don't think I was even born at that time. So
what's the big deal?
I know that's I got my start in networking maintaining ATM and frame relay switches. So.
Yeah, that's some crazy stuff. Yeah, so exactly like you said, right? So we're moving away from circuit switching. We're moving to bidirectional packet switching infrastructure, but which is largely non-oversubscribed. Like you said, of course, we can oversubscribe it, but we're no longer limited to trying to match my inputs and outputs to ensure, an inbound call does get an output line, which was necessary for telephony systems back in the day, right? And then the other thing about this architecture is it's very easy for me to scale out because this just acts as a model for me to increase my infrastructure based on the demand of my services. So I can just add more spines if I need to add more spines. If I need more speeds and feeds, I can essentially add more leafs at the leaf layer, and it's very easy to scale out this architecture.
And the boundaries are pretty much, the number of spines you can have is basically limited by how many uplinks your leaves have, and how many leaves you can have is limited by how many downlinks your spine has. Correct.
And we see that a lot with, like, if you're building AI clusters, for example, today, right? Again, like rail optimized AI clusters, for example. This is I think exactly the logic that you try to follow, where I divide my downlinks to my GPUs, and I have my rail connectors, which are my spines, as my uplinks. And you're obviously trying to do 1:1 in that specific case. But yeah, you're absolutely right, Jeff. So in such a design, what you're essentially doing is you're dividing your infrastructure into two layers. And again, this is not really a necessity, but even though we're evolving from a network infrastructure point of view, a lot of our applications still may require layer 2 connectivity, right? And then how do I provide layer 2 extension over this infrastructure if I have only L3 uplinks from my leaves? This is where you start to get into the weeds of what is my underlay, what is my overlay, what exactly is the separation, and what are the two of them doing together, right? So when you talk about the underlay, you're essentially, the goal of the underlay is I just need to provide loopback to loopback reachability in a highly available manner. For example, in case I do have failures, and I have my overlay, which essentially form my tunnel from one leaf to the other, right? And these leaves are typically called as VTEPs, which are your VXLAN tunnel endpoints, essentially saying that these nodes are capable of doing VXLAN encapsulation and decapsulation. Obviously, there's a lot of debate on what the underlay design should be like, what the overlay design should be like. And I'll throw some out there. I don't think we have to really get into the weeds of it, but different vendors do different things. For example, Juniper will largely push an EBGP over EBGP design. So you have EBGP between your physical point-to-point interfaces on the leaves and the spines, only to advertise the loopbacks. And then I have EBGP again for the overlay for L2VPN, EVPN address family between my loopbacks of the leaves and the spines, right?
I think specifically to Juniper, it's partly to blame myself and Jeff when we done some apps. I did my best to kill in 6 months any other variations. That's the most efficient, most easy to deploy to manage design.
Yeah,
so we are to blame.
Yeah. Well, is it? Would you say it's the most widely supported?
That's also what I'm building.
Approach now.
Any AI cluster that uses my designs, and they're pretty large, they use exactly that.
Okay, yeah, because you guys are both with Nokia now. Sorry, NVIDIA.
Yeah.
And is that pretty much standard practice there also?
Yeah, I think another thing you might do from optimization perspective. So spines are really needed to distribute information among leaves. So you might ask yourself, if I have 64 spines, do I really need 64 copies of the same BGP update? And the answer is probably no. You want to be resilient, so maybe you want 2, maybe 4, but definitely not 64. So you might actually optimize and have some kind of election. You could use router ID or similar semantics to choose a group of spines that are responsible for distributing all this information. But it really doesn't belong on spines. There's no reason, and it creates some inefficiency in the amount of BGP paths and some others. So if you're optimizing, think about using less spines to distribute all this information. Choose a group.
Yeah, I agree. Good to know you guys were the source of EBGP or EBGP. I've spent years and years doing that. So very interesting. Some very interesting history there. If you don't want to do that, I think a lot of people are also doing just BGP unnumbered. So you just use V6 link local addressing between your spines and your leaves for the underlay. And then you ride all address families on top of that. So V4, V6, EVPN. Of course, that requires some modification in terms of I want to make sure my spines do not change my next hop, especially for the EVPN routes, because you don't want your spines to become tunnel termination points. They should only be the leaves or the VTEPs. Or, for example, Cisco will generally recommend some form of IGP, OSPF or ISIS, and then IBGP in the overlay with some route reflectors, typically on the spines, right? Again, I've seen a lot of fun/heated debates around this, so we will try to avoid getting into that. But you do have a lot of options depending on what you're comfortable with, what you think makes sense.
So usually you see this variability in kind of enterprises on the smaller side, where people build the stuff based on their prior experiences and kind of tribal knowledge. As you go towards larger deployments, usually they're pretty standardized around design that you've shown.
Yeah. Now to scale, to further scale the network infrastructure, we do have other potential designs moving. Again, it models what you already have with a 3-stage fabric, but what it does, it starts to couple a 3-stage fabric into something called as a pod, and then you have multiple pods essentially. And then how do we connect these pods? We add another layer called as a super spine, and all your intra-pod traffic essentially stays within their own individual pods. But at any point you have inter-pod traffic, it goes up to your super spines, which provide, again, a very similar equal cost fan-out connectivity that the spines do within the pod. The super spines essentially do it between pods, right? And then the last thing, again, very small scale designs. If you're moving away from STP and MC-LAG, this is something I've seen in the wild too. The terminology is questionable, but mostly I've seen this called as a collapsed spine or a collapsed leaf design, where you're essentially collapsing the role of the spine and the leaf into a single layer. And then you have a lot of top of rack switches essentially connected downstream as multi-homed Ethernet segments, right? All right. Now, from a services point of view, obviously we can offer multiple services once you have this architecture in place. We can have L2 extension over this routed fabric, which again, you're essentially extending a single VLAN over this routed infrastructure through certain means. Obviously, with EVPN, you can also do layer 3. I know, Jeff, you don't like this at all, but I have this in here, which is old school CRB, which is centrally routed bridging, where you would consolidate and centralize all of your routing at a central point, which are typically the spines. Or
CRB came around, right?
I do not.
Oh, I can tell you. Let's sell the more expensive large switches at spine level. I mean, architecture-wise, it makes absolutely no sense. If you're in sales, however, you might look at it very differently.
I remember now. Yeah. So Juniper would sell QFX 10Ks, for example, as the spines. Yeah, and then all the super low end QFX 5Ks that could only do like layer 2 Tomahawk 2 sort of switches, or Trident 2 sort of switches, which could not do VXLAN routing, right?
And part of the driving principle, really, for ERB is you want to keep the spine as simple and dumb as possible. It should just basically do very little except forwarding packets.
Yeah, I agree. So with ERB, you move all of your logic to as close to the hosts and the edges as possible, which are your leaves, and the spines are doing absolutely nothing apart from just routing traffic from one VTEP to the other, pure IP, and just pure IP forwarders. That's it, right? So this is the general basis of what EVP and VXLAN fabrics look like. I am going to quickly skip ahead so that we can get into the meat of the intra VLAN multicast stuff.
I would like to add only one more point to that. It's how prominently VPN has become as L3 VPN. And the reason it's interesting because if you look back into times of when LTP was designed, the underlying assumption has always been that your non-directly connected next hop is MPLS encapsulated. That's why, if you look again a bit back, even when outer encapsulation wasn't MPLS, MPLS was always in the packet because L3 VPN mandates MPLS. So you would have kind of MPLS over UDP, for example, right?
Yeah.
So practically, what EVPN is, it's L3 VPN with IP next hop because VXLAN is IP. So this is what led to really massive deployments of EVPN
adoption.
Yes.
Yeah.
Just, again, it removes this exceptional treatment of labels next hop. This could be just an IP address, and that was an amazing decision to do so. And this has led to really what the VPN is today, outside of layer 2.
Yeah, it's very interesting because I think like EVP and VXLAN, especially in the DC side of things, started become very, very, very prominent. At least I saw it predominantly around maybe 2010 and above, right? And I was in Cisco TAC days where I was still troubleshooting STP day in and day out. And I could see around 2014, 2015, like a lot of VXLAN starting to creep up. But then jump a few years, that's all I see now, which is a huge uptick in how well it has been adopted. Cool. So that was a quick trip, or not so quick trip down memory lane. Now, what we want to cover for the rest of the session, I think we'll try to stick with intra VLAN, multicast, EVP, and VXLAN fabrics. So if I have layer 2 services that want to talk to each other over multicast, how do I actually achieve that in an EVP and VXLAN fabric, right? And it also has a little bit of broader scope because some of the technologies that we'll talk about not just deal with multicast, but they deal with bump traffic in general, which is the entire class of multi-destination traffic, which is broadcast, unknown unicast, and multicast, right? Now, specifically with broadcast, when you look at, we've had technologies such as ARP suppression and proxy ARP, coupled together. They can typically limit how much of broadcast you actually flood into your infrastructure, because as long as I have hosts that are being learned in my EVPN VXLAN fabric, and I'm able to disseminate that information through EVPN type 2 routes, MAC plus IP routes, I can have my VTEPs essentially build this MAC IP binding, and I can use that to respond to any ARP request and essentially suppress that ARP request from being flooded in the fabric, right? But obviously there are instances where I still have to flood broadcast packets, or multicast again is a pretty good example. And these multi-destination packets essentially have to reach all of the VTEPs behind which the bridge domain or the VNI or the VLAN exists, right? There are multiple ways of achieving this. Like you could have a static definition of all of your VTEPs, which obviously doesn't scale very well. You could have ingress replication, again, which is a fairly popular way of doing this. And we do this through EVPN type 3 routes. So as soon as I define a VLAN VNI association on a VTEP, I can advertise an EVPN type 3 route that essentially tells any peer VTEP that I am interested in receiving multi-destination traffic for this segment, right?
If I mind,
or you could.
Just a second, I think it's important to explain why this is an attribute of layer 2 networking and why potentially you shouldn't be using it, right? EVI instance is nothing else, or EVPN instance nothing else than layer 2 bridge.
Yeah.
It behaves like layer 2 bridge for all practical reasons. So what do you do on bridge when you receive unknown multicast or broadcast traffic? You flood it out of all ports beside the port you have received it from. That's exactly what replication does here. It emulates layer 2 bridge. So when you decide whether you decide layer 2 or layer 3 EVPN, this is one of very serious considerations, and it always affects your scalability, because replication of traffic, especially if you use ingress replication, usually is the first resource you run out of.
Yeah, I agree. And then of course you have multicast in the underlay itself, which you can also use for multi-destination replication, right? So similar to ingress replication, when you have like a VLAN VNI association, instead of generating an EVPN type 3 route, I essentially have my underlay enabled for PIM, and I'm able to generate these Chatterjee joins towards my RPs, which again, maybe typically they're just spines. And I can start to build this shared tree where all my VTEPs that are interested in the same bridge domain have shown interest, and we're all rooted at the RP. And then once I actually receive a broadcast, that VTEP becomes becomes the source, and I start following my multicast tree to send it to all of my interested VTEPs, right? Now, if you see, ingress replication is still quite predominant in a lot of infrastructures. And like Jeff said earlier, it is quite problematic if you stick to traditional ingress replication behavior, right? Because by default, the flooding nature of an EVPN VXLAN fabric is it's just one big layer 2 switch, right? So I get a broadcast or a multicast packet in, and I essentially flooded in all of my ports that are part of the same bridge domain, right? So this is essentially a packet capture which shows what your typical ingress replication behavior would look like for like some flooded packets, and I am essentially flooding it to all VTEPs that I know of that have indicated that they're interested in this particular bridge domain, right? So just imagine I have, let's say, 100 packets per second that comes into a particular VTAP. And I have 4 other VTAPs that have shown interest in that particular bridge domain to receive multi-destination traffic. That 100 PPS essentially becomes 400 PPS through ingress replication as soon as I start to flood it and send it into the core, right? Obviously, that doesn't really scale very well, and it can be fairly problematic as you start to scale up your network infrastructure, right? And visually, this is what it looks like. I have a packet coming into leaf 1, and I'm essentially flooding it to all other VTAPs that showed me interest in that particular bridge domain. So this is where I want to talk about assisted replication a little bit. Assisted replication essentially helps me achieve something very similar to what a multicast distribution tree does natively, but it does so in the situation that you don't want to run multicast in the underlay due to whatever complexity you think it introduces in your infrastructure. Maybe there's a competency gap. Maybe your operators are not very comfortable doing it, and you want to stick to ingress replication, but you obviously want to limit the drawbacks of ingress replication, right? So this was defined in 9574. Now, the idea behind ingress assisted replication is I want to focus on solving the inefficiencies of ingress replication by moving the burden of replication from my ingress leaf or the ingress VTAP to a operator or user nominated node in the infrastructure, right? So typically this node will obviously be more centrally located with a view of all of my other VTAPs. And it's a more beefy node. For example, it can handle replication of packets at a much higher throughput. And what you're doing here, which is what I've shown here visually, is when you receive a bump packet, let's say an ARP request, for example, instead of replicating it to every other VTAP by the ingress leaf, I will send only one copy to this user nominated node. And this user nominated node will essentially replicate it to all of my other interested VTAPs, right? So we introduce a couple of new terminologies here. You have an assisted replication leaf, which is a VTAP or a leaf which is capable of participating in assisted replication. And then you have an assisted replication replicator, which is your AR replicator, which is your user nominated node, which will receive a single copy of a multi-destination traffic, and its job is to replicate it to all other interested VTAPs.
When I look at this, it looks immediately like CRB, right? Again, you need a beeper switch that has this magic ability to replicate on behalf of less capable brothers.
Yeah, that was the thing I was thinking too, is that this sort of contradicts what we had said just, exactly. I think on the previous slide about we want the spine to be as simple as possible, and all of a sudden here we are giving it more responsibilities.
And from operational efficiency perspective, you want to be really homogeneous across switches you deploy, their functionality and ability.
Yeah, and the terminologies are a little bit of a tongue twister, so it's not easy to say assisted replication replicator. You should try saying that a few times.
You sound like really a pirate.
Yeah. Yeah, I should have worn an eye patch for this one. But we are going to stick with this for a little bit because I think it's still an important topic. Unfortunately, because a lot of vendors don't support multicast in the underlay. So assisted replication. You're essentially taking the same EVPN type 3 route, which you use to show interest in a particular bridge domain, but you're adding some additional information in this, right? So you add like an assisted replication type, which indicates what kind of role I am in. Am I an AR leaf? Am I an AR replicator? And you have a very specific tunnel type or a tunnel ID, which tells me that this EVPN type 3 route is actually for assisted replication and not for ingress replication, right? Now, once you nominate an assisted an ARR, it is obviously responsible for generating new EVPN type 3 routes, where it defines itself as an assisted replication replicator, and it's also defining a new assisted replication IP address, which, depending on the vendor, can be different from the ingress replication IP address, right? And we'll talk about that situation really shortly. What that does for my assisted replication capable leafs is, now instead of having a flooding list that lists all of my remote VTEPs that were interested in bump traffic for this VLAN or VNI, I can now essentially consolidate that into just a grouping of assisted replication replicators. So most vendors, what they will do today is, they have a flood list. That flood list points to a next hop group, for example, and that next hop group will essentially give me like a unilist of individual next hops that take me to out of very specific tunnels to very specific VTEPs, right? So in this case, I move away from flooding to all of my remote VTEPs to only flooding to my assisted replication replicators. And this is what that packet would look like. I am just sending a single copy from my ingress VTEP that is capable of assisted replication, and I'm sending it to my assisted replication replicator's IP address in this case. Now, an important part of this obviously is, how do I support devices that are not capable of assisted replication, right? Either they've not been enabled, or their legacy device, and I can't really configure assisted replication in this case. So we take leaf 4 as an example here, and let's say I have a new source 3 that is connected behind leaf 4, right? So I'm not really capable of assisted replication in this case on leaf 4. This is where we have to figure out some forwarding rules for assisted replication. And to your point, Jeff, this is where it starts to get really complex when you're starting to build this, as you can already see, right? When an assisted replication replicator receives a broadcast on a local interface, right? So I have a local attachment circuit, just a local L2 leg with a specific VLAN. I'm essentially allowed to forward it using my flood list for all of the VTEPs that have shown interest, just using plain vanilla ingress replication, right? Now, typically my AR replicator can have 2 tunnels. I can have a tunnel using my ingress replication and the ingress replication IP address, and I can have a tunnel using my assisted replication and the assisted replication IP address, which may be a completely different IP address if the software and the hardware of the vendor allows that to be configured, right? So again, the rules are simple, but from an operation point of view, they can get complex. So if the AR replicator receives a bump packet, and if it is my ingress replication IP address, I'm not going to forward it out to any of my VTEPs that showed interest using assisted replication flags set, right? I'll only send it to my local interfaces. If I receive it in the overlay tunnel, which actually matches my AR IP destination, then I can use my AR flood list and essentially send it out to all of my VTEPs for that particular bridge domain, except obviously split horizon, except the leaf that originally sent the packet. And then I will obviously avoid replicating to other AR replicators in that particular situation, right? So using these forwarding rules, if you look at how we actually achieve backward compatibility in this case. If I have a source sending traffic to a VTAP that does not include any configuration for assisted replication, I can only replicate using ingress replication in this case. So I will send it to my ARRs. I will send it to all of my other VTAPs because I still am building my flood list through ingress replication. But then very importantly, my assisted replication replicators will not replicate this back to my VTAPs because I've received it over my ingress replication IP address, right? Moving on, we obviously have to consider some multi-homing scenarios here because there is a fairly clear possibility that traffic can loop back in such a situation. And we have typically solved this, through different means, split horizon, local bias forwarding, and stuff like that in the past. For assisted replication, it poses its own challenge. So imagine I have a source that is connected to a segment. It's a single home source, but it is connected to a leaf, which is part of an Ethernet segment. So the leaf is, let's say, it's the non-designated forwarder in this case. I will flood that to my ARR, which will flood it back to my AR leaf, which is potentially a DF for that segment. And since I'm a designated forwarder for that Ethernet segment, I am allowed to flood it back down to the node that has already received that traffic because of local bias forwarding, right? So this problem obviously had to be solved in some way or the other. So there was an IETF draft that was written up for this, where we introduce some additional complexity and a new role for assisted replication called as an extended, what is it called? An extended multi-homed AR replicator. That's what it's called, right? So the names just unfortunately get bigger. So these extended. Sorry, go ahead, Jeff.
So we are getting close to the hour, and I think it would be kind of good point to wrap up today on assisted replication.
Yeah.
And next meeting to go over more details of multicast in general, right? Because
I think we've got a long way to go. I think we've got a couple of shows ahead of us. If Aninda, if you're willing.
Yeah, of course.
Practically, I would like kind of to. Sorry.
Go ahead, Jeff. Yeah.
I said it's a fascinating technology. It's an extremely complex technology. It's error-prone, difficult to troubleshoot. I said really you need to use this, right?
Yeah.
You should always keep in mind simplicity kind of guarantees good night's sleep.
Yeah.
If you like to be up at 2 a.m., you might seriously consider not to using layer 2 in general and kind of daisy chained or hierarchical kind of replication in general. It's really, really complicated technology.
I agree. I think it goes back to a lot of the horrors of spanning tree, for example.
Yeah.
It looks and feels good to learn. Like you feel like you're learning something very technical and complex, and it sometimes scratches an itch, but do you really want this in production when you're the one responsible for it? I don't really know, right? Again, but the only reason I put this out there is I think all of these technologies will essentially help you choose what you want to run in the fabric, and that also determines the vendor, the software, the hardware, the support, and this is good to know when you're actually making some of those decisions, right? For example, if I run into a vendor that really only does this, and I want to scale out, but the only way for me to limit how much traffic is flooded is assisted replication, then maybe you think twice about actually operating in that environment, right? So I think it's good to know, it's good to learn. Do you want to operate it? Yeah, maybe not.
You always want to to make an informed decision, right? Understanding the
Yeah.
technology, understanding different technology trade-offs will allow you to actually be the best in what you do. And the more you know, the better consequences of your decision will be.
Absolutely. So I have one more slide, which is what do we actually do when we have extended multi-homed AR replicators? So what they're essentially doing in this case is, I will maintain a list of all multi-homed VTEPs, and when I actually receive purely by importing my EVPN type 1, which is my auto discovery per EVI route, because that essentially has my MAC VRF EVPN instance route target, which should exist on my AR replicators anyway, right? So I just import those. I build out a list of all of my multi-home VTEPs, so I'm fully aware of which VTEPs are actually multi-home to the same Ethernet segment. So when I receive such a packet now flooded only to me as an extended MHAR replicator, I will simply choose not to replicate this to any peer VTEP of the original ingress VTEP, and I will only replicate it to all of my other VTEPs. And then the burden of replicating to any multi-homed VTEPs falls back to my ingress VTEP itself, right? So we really go deep down that rabbit hole of complexity, I agree. But it's still a good technology to be aware of, to learn, to make informed decisions, like you said, Jeff.
Great.
We'll stop here, because from here, I think I move on to selective multicast forwarding and IGMP snooping and stuff like that, which is more common across vendors.
Yeah, and sorry, Jeff, go ahead.
That's amazing. So I think it's logically very good starting point to start from a native multicast and how it works in EVPN. So I think we are great in time and content.
Yeah. And Aninda, I'll ping you offline and would love to have you back on the next show.
I'd love to be back. Yeah, absolutely.
And probably
this is fun.
I suspect the show after that too.
Yeah.
It's always fun to have a guest go in deep for a while. So I know we've got to run. We've got kind of a hard stop here, but Aninda, thank you so much for joining us, and it's also fun just having old friends on the show.
Thanks for having me. Thanks for having me, guys. I appreciate it.
And we will see everyone on the next Between Two Nerds.
Thank you.
Thank you.